Moving right along. This one I've seen in just so many different scenarios. This is from the start of the third story arc, Kenshin. He's chilling out. There happens to be this eclipse, which was foretelling something bad or other. And it's just very slow, by anime time, I suppose. Not that anime time means anything. So you can see the moon starting to move across the sun. Kenshin's just chilling there watching it. Like, oh my gosh, the moon's moving across the sun. Like, stand there and watch this. I again trimmed this clip thanks to Ethan. Probably you guys know him, Deadly. He helped me trim a lot of this because my computer's being stupid. Overall, this whole eclipse only took, let's skip that, about 1 minute from the time where it moved, first touching the sun to in front of it to all the way off. It should take about 2 hours. Let me jump back to that last slide and say what the hell an eclipse is. Basically, you got the sun over here, you got the Earth here, and when the moon orbits around, it casts a shadow on the Earth, and then it causes an eclipse. There's two parts to the eclipse. If you're sitting over here in this lighter blue area, you can still see part of the sun. You could draw a line through the sun, so that's only a partial eclipse. It's only in this darker area where it gets really small here at Earth that you would see a total eclipse. The moon orbits the Earth every 28 days, so why is it that we don't see an eclipse every 28 days? Well, the reason is that the moon's axis is tilted slightly compared to the Earth. It's off by about ½ a degree. So sometimes when it's the point closest to the sun, it would actually be back further behind the screen or out in front of it and not casting a shadow on the Earth. It would just kind of miss the Earth. Doesn't directly pertain to what the hell I'm talking about in this panel, but I'm an astronomer and I like to talk about that stuff anyway. Alright, so going back to what I was just saying, 1 minute versus 2 hours. That means the anime moon moves about 120 times faster. My question is, what are we going to have to do to the Earth-Moon system to make that actually happen? So, breaking this down a bit more into units so we can start approaching this, I converted the real orbital period of the moon, 29 days, to seconds, so we can use systematic units. The anime orbital period, converted that to seconds. Some other units we're going to need. We're going to need the mass of the Earth, we're going to need the mass of the moon, and the distance to the moon, perihelion, which means when it's closest. When it's closer, it's moving faster, so that's why I chose that instead of when it's at its furthest or its average. Alright, so, this is a nice question. I love this one. So sexy. Newton's relation to Kepler's third law, the orbital period equals 4 pi squared a cubed. A is the semi-major axis, basically how big the radius is. G is the gravitational constant. M1 and M2 are the masses of each body. M1 we usually just, out of tradition, use to describe the larger body, so we're going to call that Earth. We can play around with a lot of things in this. We could play around with the masses of the moon. We could play around with the mass of Earth. We could play around with basically how far out it is. We can't really mess with the 4, the pi, or we can't mess with gravity, otherwise then that would kind of screw up the rest of the series if gravity was working wrong. And we had just in the last slide solved for that tau, which is the orbital period. So we got 3 things we could play with. It turns out we can't actually play with A. We can't play with the distance, because if it's closer it would look bigger and you wouldn't get that nice just covering the sun. If it was further away, then the sun would have a larger angular size and the moon would look smaller and you would never get a total eclipse. So you can't play with that. We can only play really with the mass of the Earth or the moon, and we can't end up really playing with the mass of the moon, because if we increase that too much, then we would be orbiting the moon and not the other way around. So the only thing we can really play with is the mass of the Earth, so let's solve the equation for that. And I didn't show the solving for it, but I solved for the sum and then subtracted the other out. And it turns out that you would have to get the mass of the Earth to be 1.33 times 10 to the 33 kilograms. Yay, units, what do you do? Context bowls. Let's put that in perspective. So, G is acceleration due to gravity. It actually turns out to be the gravitational constant times the mass of the body divided by the radius squared. So, G, gravitational constant times the mass of the Earth divided by how far from the center of it we are, gives us the acceleration due to gravity, which any high school physics graduate can tell you, 9.8 or 10 meters per second, depending on how accurate your teacher wanted to be. So what is it for anime land when we plug in the mass of our new anime Earth? Oh, you know, just 2.2 times 10 to the 12 meters per second. Oh, good, more units that don't mean anything to not mathy people. Again, the normal gravity is 9.8, so let's divide that out. This means you would weigh 220 billion times as much as you actually do. You would be flat like a pancake. I had done this, and the first time I did it, I actually made an error in the calculations. Last year I talked about something called dimensional analysis. I didn't do it this year. I forgot to pay attention to my units at one point, and I was off by a factor of 1 billion. Oopsie! It would have been better if that were actually right, because then the density required for that would have made us, the anime Earth, be the gravity required for a black hole. That would have been cool, but it didn't work out that way. But still, 220 billion times as much. Even the supermodels would not be looking too good. So that one ain't gonna work. All right.